Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1000. Hopefully, you guys are okay and had a good week so far. Let's actually forge ahead. So, let me share my screen here so we can get started. Let me make sure I can see the chat. Okay. All right. Okay, so we're good. As always, let's start with some public service announcements. Colleges closed for election day, which is next week, Tuesday. Go out and vote if you can. Our next class is on Monday, and on that day you have a quiz. So quiz 4 is on Monday, so you should be studying over the weekend for that. And you should cover up to lecture 16 by today. That's what the quiz is going to be up to. I believe it's lectures 14 through 16. And I'll actually talk about that in a little bit. That should not be here. I don't know why that was there. I guess I was copying the announcements from the last thing. Okay, there we go. Yeah, and our next Zoom lecture is actually on Thursday, at which time I will go over the quiz. So on Monday, you have a quiz. It covers lectures 14 through 16, and we'll go over that on Thursday. Tuesday, there's no school. If you are eligible to vote and you want to vote, you can do that on Tuesday. Moving down, as always, the quiz is on Gradescope, so log in at the beginning of the class period and take the quiz. If you're curious as to what sections it's covered, pretty much these guys here. Section 1.10, 2.1 through 2.4, 2.7, 3.1, and 3.2. There is one thing, I believe, in section 2.2 that I didn't cover here. That I covered later on, and that was piecewise functions. Okay, so piecewise functions, as that's mentioned here, that was also done in section 2.2, but I didn't cover that in these lectures yet. I covered it in the following lecture, I think lecture 17. So these are the sections for the quiz. Here are the topics. So I'm going to be quizzing you on equations of lines, the slopes of lines, their graphs, quadratic equations, their vertices, their graphs, graphing polynomials, end behavior. We also introduce functions and different ways to represent functions. So I might quiz you on stuff like that. Function operations, combining functions, creating function composition, multiplying two functions, dividing two functions, etc. As well as, again, the difference quotient and average rate of change, which those guys are just basically formulas, and you can that we've actually seen before. So if you're pretty comfortable on all that stuff and you don't want to actually move ahead, so the topics that I start talking about from lectures 17 and 18, which is where your bonus might come from, is piecewise functions, as I mentioned, transformations of functions, that's like shifting functions, inverse functions and their graphs, so we do talk about inverses, as well as I might throw in some more questions about like circles and Pythagoras' theorem and distance formula and all that stuff, because I wanted to officially include that on this quiz, but I made a typo in the syllabus and I just noticed that it was, I just noticed that typo last night, so I didn't think it was fair to just like throw in section 13, lecture 13 as well. So I'll just move those guys to the bonus section again. So in a perfect world, the quiz would have been on lectures 13 through 16, but because of the typo in the syllabus that I noticed very late, it's on 14 through 16. So as for lecture 13, it's stuff that we've seen already. I believe I threw in bonus problems on that section on quiz 3 as well as test 1. And I'll throw in some more bonus problems on this quiz because it's important stuff you should know, but we never really had it officially on any quiz yet. So that is pretty much where we are. I think we're kind of up to date with everything. And yeah, so that's basically it. Now we're going to do the Q&A session. I just separated the topics here. For the most part, and you guys can correct me if I'm wrong, I think almost everyone would be okay with the equations of lines and slopes and graphing lines and all that good stuff, as well as the difference quotient and average rate of change. Those guys are just knowing two formulas. But you might want to ask me about the other topics, or even these topics. If there's something here that you're not comfortable with, we can deal with that as well. So right now, just the Q&A session. Anything that was discussed in the lectures that you had questions on, we can talk about that. So questions? Or about anything else in the class, I would suppose. Questions, issues, comments? So we're all good on all these topics? We're experts? I could give you the quiz today. Yes, no, maybe so. Is anyone alive out there? People do. It's like we have about 17, so there are some people missing. Okay, let's talk about these since no one has any questions. Move this to the side. All right, so let's talk about quadratic equations, their vertices, and all that good stuff. Okay, so I ask you to solve, let's do some concept checks here. Let's talk about solving quadratic equations. Okay, so given ax squared plus bx plus c equals 0, a is not equal to 0, to solve for x, tell me about solving for quadratics. I give you a random quadratic equation. I ask you to solve the equation. Tell me in your mind what is the first thing you would try to do, the second thing you would try to do, third thing you would try to do, etc. Just tell me like the strategy.
Wouldn't you start by factoring?
Okay. So one, try to factor left side. What do you and what would you do after that?
You would set the factors equal to 0, like each set of factors.
Okay, so that's one strategy, probably the first thing you would think about. And of course, factoring would be different based on the fact whether your A is 1 or it's not 1. So you might have to do the AC method or one of the other methods that we spoke about, but that's basically how you do it. What if it couldn't factor? Because not all quadratic can factor.
Would you do the quadratic formula?
Right. So then you try quadratic formula. Now, again, the quadratic formula always works, but for some it's overkill. Like you'd waste time actually doing it. So I wouldn't recommend you do that first. So this here always works, but can be overkill. Okay. And so, yeah, those are the two main strategies for quadratic equations. There is a third strategy, which is completing the square, but I wouldn't really recommend doing that to solve a quadratic equation. It is a skill that you need to know anyway, but I wouldn't particularly use that skill in a situation like this. What if I ask you to graph a quadratic equation? Tell me about that. Ask you to graph this. What do you do?
Check to see if A is positive or negative.
Okay. So if A is positive, what does that tell you?
It opens upward.
And if A is negative, it opens downwards. So yeah, one thing you can have the shape in mind. So you can identify the shape as a step 0. Okay. Then what? So you know it opens up or down. How do you actually get it on the picture? Okay, come on. You guys didn't have any questions, which means you should know everything. How do you actually get the picture drawn? So I know it should open up or down. How do I know where to draw it? How to draw it?
See if there's X intercepts and then find the Y intercept.
Find the intercepts would be the next thing. So you'd find, if you look for the X intercepts, how do you find the end X intercepts?
Would you set y equal to 0?
You set Y equals 0, solve for X. So that means you want to basically solve ax squared plus bx plus c equals 0. And we've already discussed how to actually do that. Okay, what about the y-intercept?
Set x equal to 0.
You set x equals 0, solve for y. Right, which is, it's always going to be basically y equals c, right? Because you just plug in x equals 0 everywhere. Okay, so you find those and you would plot them, right? So example, let's say your x-intercepts are x equals 1 and say x equals 3, and y-intercept is y equals -2. Then using the intercepts, you can go in and you know your graph is just going to look like that, where this here is -2, this here is 1, this here is 3. Notice here, and this is why I really looked at the intercepts as step 1. If you actually find the intercepts correctly, then it's actually going to force you into drawing it in the right direction. So this particular kind of example, notice that I can tell you that my A was negative without even knowing what the equation is. And that's just because to actually draw the shape through these 3 points, it had to open downward, okay? So even if you don't even identify the A, whether it's positive or negative, so you know it opens upward or down, just by finding all the intercepts, provided that there are 3 of them, you can actually figure that out. You can use your A to double check, but there are other situations in which your A is going to be very important. So, well, not really, even in those cases. So you'll always have a y-intercept, but you might not have x-intercepts. So let's actually talk about that. So here, what if we don't have x-intercepts? So you go in, you try to find the x-intercept. It can't factor. So you try to use a quadratic formula or whatever. You did it, but you get a negative under the radical, which means there's no real solution. So you don't have x-intercepts, which is very possible. What do you do then?
You find the vertex.
Right. So here you would find the vertex. How would you find the vertex?
Is it b over 2a?
No, but close.
Oh, negative b over 2a.
Okay, a little bit more specific.
X equals negative b over 2a.
X equals negative b over 2a. You need to know, who are you solving for? Who's negative b over 2a? So x would be negative b over 2a. X b equals negative b over 2a for vertex. Then you can plug this in to find y, okay? Or you can actually complete the square. So you would have your quadratic would look something like this. And then your vertex would be the coordinate h comma k. So you'd have a couple of different situations here. let's maybe do an example. Let's say I ask you to graph y equals x squared plus 2x plus 7. Okay. So now you go and you try to find the intercepts. Right? So you set x squared plus 2x plus 7 equals 0. Doesn't actually factor, so you plug into the quadratic formula, minus b plus or minus the square root of b squared minus 2ac all over 2a. And here you realize that there's a negative. So this means you have no x-intercepts. Now, there are a couple ways you can actually work around this, as we've been talking about. So one way is to find vertex. So once you realize you're in this situation, okay, I did this, I'm finding my intercepts, but there are no x-intercepts. So what I would do is first find vertex. Two ways to go about that. The first way is you let x equals minus b over 2a. So in this case, your x would be minus 2 over 2 times 1. So your x would be minus 1. And then you would plug this in. This means that your y would be minus 1 squared plus 2 times minus 1 plus 7. Okay, so that's 1 minus 2 plus 7. So that's 6. And so you know your vertex is minus 1 comma 6. The other way is to actually, if you can go back to the y squared plus 2x plus 7, and you can complete the square. So you know that you take half the coefficient of the x term and square it. If I multiply this out, I would get a plus 1. To get back to plus 7, I need to add a plus 6. So this looks like 1 times x minus a minus 1 squared plus 6. And so your vertex, which you don't have to write down that line, but you can see here the vertex is going to be minus 1 comma 6. So either way, then you would find the y-intercept. This is just 7. So now you actually can go and graph. So your vertex is minus 1 comma 6, which is here. And then now you know it opens upwards. And it crosses here at 7. So you can sketch the graph like that.
Is it okay to only graph 2 points? Or should we normally have 3? Because I just didn't know how we would get like 3 in this situation. So I was wondering if it would.
No, you'd only graph these 2.
Okay.
So you'd only graph the vertex and the y-intercept. So the situation where you'd expect it to be identify 3 points would be if you have 2 x-intercepts and a y-intercept. And usually in this case, I wouldn't require you to identify the vertex. Although, what is the x value of the vertex on this example? Hello?
Could it be 2?
Are you guessing?
Yeah. I thought it was like.
Well,
just like
you shouldn't be guessing.
Yeah.
This is a concept that we actually spoke about for parabolas. If they have 2 x-intercepts, the vertex always occurs smack dab in the middle between them. So in the middle between 1 and 3 is 2. So the x-coordinate for the vertex is going to be 2. And then you'd find the y value if I gave you the equation. And remember, this is not true in general, which means if you have a cubic or anything larger than a quadratic, and you have like two intercepts, you can't assume that the highest or the lowest point is right in between the middle of those two. For quadratics, this is true, but it's not true for general functions. So that was also a concept that we spoke about. So yeah, that's graphing quadratics, and that's about their vertices. What about graphing? Graphing general polynomials and end behavior. So tell me about that. I give you a polynomial. What do you? How do you go about graphing it? What do you look at?
Would you start off by finding the zeros of a polynomial?
Right. Which again, find the intercepts would be your step one. Right. Same way as before. Same as before. So x-intercept, set y equals 0, solve for x. Y-intercept, set x equals 0, solve for y. That's just how you find x and y intercepts in general. So that's the first thing you would do. Now, once you find those intercepts, now what?
Can't you look at A to see the M behavior?
You look at A,
Oh, not A, N.
N is the highest power. Sure, we can leave that off for now, though. I'll ask you about N behavior specifically later on. So you find the intercepts. What's the next thing you would need? What do you do then? How come you guys didn't have any questions for me in the beginning? It's like now I'm asking you very basic concepts and you're, are you just shy? You don't have to be shy, speak up. So the next thing you would do is you would plug in values, or let me be specific, plug in x values in between the intercepts to see where the graph is above or below x-axis. And then what you do is you just you would sketch a curve passing through all intercepts obeying the positions found in the previous step. Okay, so that's how you'd actually graph them. So maybe let's do an example of that. So let's say I gave you, and I'm just making up examples off the top of my head here. Example, graph y equals 5 times x squared minus 1 times x plus 2 times x minus 3 squared. Okay. So I tell you that, right? So I just throw this out there. So go through the steps with me. First thing what we would do is what? Intercepts. Tell me about the intercepts. What are the x-intercepts?
1, -1, -2, and 3.
Okay. What are the y-intercepts?
Wouldn't -3 also be, oh wait, never mind.
What is the y-intercept? So go back to the concepts, right? If you're confused about something, there's a simple concept that you're missing. So go back to the concept of a y-intercept. If I want to find the y-intercept, what is it that I have to do? What is the strategy? What is the concept? How do I find the y-intercept? What did we say?
You would set all the x's equal to 0.
Set all the x's equal to 0. Okay, so your y would be, if I plug in x equals 0, that's a -1, plug in x equals 0, that's a 2, plug in x equals 0, that's a -3. Right? So that's going to be 9 times 2, which is 18, times a -5. Or I can think of it as, that's going to be 90, right? 5 times 2 is 10 times the 9. So it's -90. Okay. So now 2 is when you go and you plot all these intercepts, right? So our x's were -1, -2, 1, and 3. And the y-intercept was, it's not drawn to scale, obviously, -90. What we do is we go in and we plug in numbers in between these guys to see where the graph should be. So you would have, you can, and again, the end behavior can save you from having to do these. So let me, maybe I should put that in a different color. So over here, I can say plug in a -3. And over here, I can plug in, say, a 4. And I'm really just plugging into the original graph to see what I want to get. And here I can plug in, say, a -1.5. Here I can plug in, say, a -0.5. Here I can plug in, say, a 0.5. Here I can plug in, say, 2, right? and we go and we plug it back into the original equation, right? So let me move this here so we can. Just moving this here so I can see. And then we'll talk about the end behavior as well as an additional thing that you can do. But technically to graph it, you don't even need to know the end behavior in the beginning. So yeah, so I'm just gonna now plug in numbers. So now if I plug in -3, for example, right? So if I plug in -3, of course the 5 is always gonna be positive, so I'm not gonna care about that. So this part is gonna be positive. This part is gonna be negative. This part is gonna be positive. Also, the square is always gonna be positive. So I only care about the signs of these two, right? That this is always gonna be positive and this is always gonna be positive. So now overall it's negative. So I know that my graph should be below the x-axis. So I just mark, X marks a spot, doesn't matter where, you just wanna identify, should it be above or below, okay? Now, notice that if I had plugged in the 4, this would be, the first factor would be positive, second factor would be positive as well. So the graph should actually be on top for the 4. So I just mark that off. And now I just go through just like that. So -1.5. So if I take 1.5 squared, that's bigger than 1. So this part is going to be positive. -1.5, this part is going to be positive. And so that's positive. It's above the x-axis. Plug in -0.5. This is going to be negative. This one is going to be positive. And so I should be below the x-axis. Then I plug in +0.5. This is going to be negative. This is going to be positive. We actually didn't need those. I could have just plugged in one of those. The intercepts were -1 and 1, so I already have that. Then I move on to 2. 2 is where we're at. If I plug in 2 here, that is going to be positive and positive. So I know I should be up here. Okay. So now I have all of that, right? By just plugging in the values. So now I know that in the far left, my graph should be below, then it goes above, then it goes below, then it goes back above. Then I have to touch the 3 because it's an intercept, but I stay above. So now I have that graph, right? Now, here's where the parenthetical statement comes in. End behavior can be used to figure out the green X's marked above. Right, so you can use the end behavior to save yourself a couple calculations. We'll talk about end behavior in a little bit. What I want to do now is show you how to fill in these guys. Now, once you have that, three. Now you're going to do the sketch. And you just make sure it's wavy going through, because polynomials are very wavy, very bubbly functions. And we just need to make sure that we pass through all the intercepts. So we definitely have to hit here, we have to hit here, we have to hit here, we have to hit here, and we have to hit here. And I know on the left I should be below, then I go above, then below, then above, then I stay above. So the graph would have to look like that, that, that. Now we don't know how far this dips. Like we don't know the minimum. Right, it could be dip a little before the y-axis or a little after, but if you draw anything resembling this, I would give you credit for it, right? So that's what this graph would look like, right?
I have a quick question.
Yes.
So going back to the original equation about the M behavior, just because I thought it would look different. I remember like in the video, there was a problem like this and we were like supposed to add up all the exponents to get like a sum.
Right.
So it would be 6. So is like,
It would
wouldn't the
not be
two-
6. You're miscounting. You're miscounting. The power would be 5.
Okay.
Right? So let's talk about n behavior, and we can copy this example as an example. Let's go over n behavior and then we'll talk about this. Okay, so now n behavior. So n behavior, we can identify this for polynomials using the degree of the polynomial. And that's the degree of the polynomial. This just means the highest power. Of x. Okay. And we had the idea was if highest power is n, then there were a couple different scenarios, right? So technically they're around 4 if we count the coefficients. So let's say I have one, n is even. It's going to behave a different way from if n is odd. So like an x to the 5th versus an x to the 8th or something like that. Okay, so if you have something like an ax to the n and your a is positive, then that means the n behavior is the following. Both sides of the graph will go up. So you can say as x approaches infinity, y will approach infinity, and as x approaches negative infinity, y will approach negative infinity. So you can say that. So you can say as x approaches infinity, y approaches infinity, and as x approaches negative infinity, the y also approaches infinity. Y keeps going up no matter if x goes to the far to the right or far to the left. The opposite happens if your a is negative, then both sides will go down. Create some space here. So as x approaches infinity, my y would go down. And as x approaches negative infinity, my y also goes down. So both sides would do the same thing in the even case. Or if negative coefficient. So either both sides would go up or both sides would go down, depending on if the leading coefficient is positive or negative. But both sides basically do the same thing in an even graph. If you are odd, so you're ax to the n and you have a is positive, both sides actually do the opposite. So you'll have one side going up, specifically the right side if your coefficient is positive, and the left side will go down. So you would have as x approaches infinity, the y will approach infinity, but as your x approaches negative infinity, your y will also approach negative infinity. Both x and y will go down, or they'll both go up, or if negative coefficient, your ax to the n and your a is less than 0. And again, we're in the thing that n is odd, remember? Then again, the sides will have like seemingly opposite behaviors. So in this case, the left side would go up, but the right side would go down. So you'd have as x approaches infinity, your y will approach negative infinity. And as x approaches negative infinity, your y will approach positive infinity. So these are the n behaviors. Now, in our above example, we had this guy. We can, since we're multiplying, laws of exponents tell us we sum the highest power of x in each factor to find the degree. So that gives us the degree is going to be 2 plus 1 plus 2. So the highest power in the x squared minus 1 factor is 2. The highest power in the x plus 2 factor is 1, x to the 1. And for the x minus 3 all squared, if I were to multiply this out, the highest power of x will be the square, it would be 2. So the degree is 5. And the coefficient is positive 5. So I know my y would be equal to 5x to the 5th plus a whole bunch of other stuff. But we don't really care about the whole bunch of other stuff when we're doing the n behavior. So this kind of tells you that the right side should go up and the left side should go down, and that's the n behavior. And this agrees with our previous graph. So basically you see that I tested, and I know that on the far left, my graph had to be underneath the x-axis, and the far right, my graph had to be above the x-axis. I didn't have to do those calculations. What I could have just noticed is that the highest power is a 5, and the coefficient is positive. Therefore, the right side needs to be going up and the left side needs to be going down. So I know that on the far left, it has to be below the x-axis, and on the far right has to be above the x-axis. So I could actually save myself some calculations there. But in terms of n behavior, you can determine that by the degree of the polynomial. About functions and their representations. You have a lot of time, so maybe I'll at the same time. I mean, these also, we've kind of been dealing with functions, even though we never formally defined them. And I think a lot of you are also familiar with functions. So the ways we saw of representing them was with so functions, these are rules so that exactly one output is assigned to each input, right? So you have a set of things that you call the set of inputs. You call this the domain of the function. Each of those guys get, they are assigned one person, exactly one person in the set of outputs. So you're sort of making connections between these two guys, but you only connect one person to each element of the domain. And we looked at the precise definition of this, and we did examples in class. So we saw that you could represent these by formulas. So when you look at representations, you could use formulas, could use graphs, could use table of values, could use mapping diagrams. You could use words. Was there another one? I feel like I spoke about 6 things, but these 2 were the most important ones. Those are the ones that we can manipulate very well in a class like this. So you should know how to plot the graph of a function in the formula. So formula is like you're writing y equals f of x, right? So example, y equals 2 over x plus 1 is the example of a function. And when it comes to operations, this is just talking about how we can combine functions. So we can have like f of x and g of x are functions. Then we can do things like multiply them. So we call this the f of g of x. And this is just f of x times g of x. And you multiply out and expand parentheses. We described this process already. So I don't have to do that again. You can have a division function where you just take the one function and divide by another function. And this, of course, your denominator cannot be 0. You can have the sum of the functions, which means you just add their output formulas. Can work for subtraction as well. And we had something that's called the composition. Very important. This is the guy that looks like F circle G, pronounced F of G. And this is basically you take F and everywhere you see X, replace it with G. So in F, replace all X with parentheses G of X. Okay, so that was the composition. Yeah, and we did a lot of examples like that. The difference quotient is an example of using a composition because you have like the f of x plus h. It's like your g is x plus h, right? Composition is what people often mix up, even though I was trying to define it carefully. So you have like a 2x squared minus x plus 1, and say your g of x is x minus 1. Then I can talk about f of g of x. That just means I go into f, and everywhere I see an x, I now put instead a g in that position. And so basically that looks like 2 times x minus 1 squared minus x minus 1 plus 1. Right, and I can multiply out and simplify that if I want to. But that's sort of the composition. And I can ask you about evaluating this function at a specific point. So say we want f of g of 2. And there are a couple ways that we could do that. So you can first find g of 2. Then plug into f. Okay, so you would have g of 2. This would be 2 minus 1 equals 1. Then you would find f of g of 2. Well, that's just the same as f of 1. And so you just go to the f and you plug in 1. 2 times 1 squared minus 1 plus 1. And so you get 2. Or you can first find f of g of x, then plug in x equals 2. So we saw earlier that f of g of x was 2 times x minus 1 squared minus x minus 1 plus 1. This means f of g of 2 is going to plug in 2 for x. So that just becomes 2 times 1 minus 1 plus 1. You get 2 again. So this second version, this is recommended if you must reuse f of g, right? So if I just ask you about one point, like, okay, find f of g of 5, and I never ask you to do anything with f of g ever again, then you could just actually do the method on the left. However, if I ask you about f of g at a bunch of different places, it will be better for you to find the general formula and then just plug in the different x's, right? So neither of these is more correct than the other, but one might be a little bit more annoying to apply than the other if you have to be reusing the function. The other combinations of functions, students tend to be okay with. And also, yeah, equations of lines, like I said, everyone should remember that the difference quotient and average rate of change, should remember that. But the other concepts we just spoke about, these are the things you'll be quizzed on. Any questions? Yeah. Okay, I guess we can end there since there are no more questions. Yeah. So that's it. So you have a quiz on Monday covering all this stuff, and no college on Tuesday because election day. And then we'll go over the quiz on Thursday's class in a Zoom class. That being said, I will let you guys go right now. Have a good weekend, study hard, and I guess I'll see you guys in the next one. Ciao.